excuse me, I made a small mistake here. L max is with respect to the non-extended code. So L max is equal to max over x of L of x, which is of the non-extended code. So of the extended code, the length of the longest possible code word is if I take, this is the kth extension. So the length of the longest possible code word is k of the longest possible code word. So this is actually k L max. L max is of the original code, which is not extended, then an extended k times. So if I have a code, if I have an extended code word consisting of the k longest code words in a row, which is possible, then the longest possible code word here is k L max of the kth extension.
Excuse me.
Yes?
The notation max x Lx, why you used it once again in the previous notes I saw. That means the argument which, or how should I interpret that?
It's the maximum over all the possible x's. So I guess you could say over x in the sample space of the random variable x of the lengths.
So it's maximizing length, not the argument.
Correct.
Okay.
Okay, sorry about that. That should have been k L max, and now I'm back. So this is equal to the sum from I equals 1 to k L max of 1, which is equal to k L max. So in other words, this to the kth power is less than or equal to k L max. Let me write that up here. Let's take the kth root of both sides. Now remember, I'm taking kth extension. K is just, k did not appear in the statement of the theorem, so therefore I'm free to choose any value of k that I like. And in particular, the limit as k goes to infinity of k L max 1 over k is equal to 1. So if I pick k going to infinity, this must be true for all k, so therefore if I pick k going to infinity, it must be true that the sum over x 2 to the minus Lx is less than or equal to 1, which is the Kraft inequality. Okay, it was a fairly complicated proof, but this led to, just to review, this led to a property of k-fold extensions of the code word. And what we did was we counted all of the possible numbers of code words with a certain size. We showed that because the code word is uniquely decodable, the numbers of those code words with each length was limited because it had to be less than or equal to 2 to the I. Otherwise, the code would be singular, which led to this statement. Now, because I can pick k equal to anything, I can pick k as large as I like, and in fact I can force k to go to infinity, so therefore it must be true that because this limit is 1, it must be true that this sum is less than or equal to 1. So, the moral of the story is there are no uniquely decodable codes with L of C smaller than h of x. You'll remember that we proved last time that for all codes satisfying the Kraft inequality, we must have h of x less than or equal to L of C. And all uniquely decodable codes must satisfy the Kraft inequality by this theorem. So therefore, this also holds for uniquely decodable codes that do not, that are not prefix codes. The second moral of the story is that nothing is lost by using prefix codes. Nothing is lost by using prefix codes. So this tells us that both prefix codes and non-prefix but uniquely decodable codes must both satisfy the Kraft inequality. So because nothing is really lost by using prefix codes, and prefix codes are easier to use, from now on we're just going to use prefix codes. Any questions about that? So next time, I was hoping to get to it today, but I've run out of time. Next time we'll talk about the Huffman procedure, and the Huffman procedure, given a certain probability distribution, the Huffman procedure will give you a prefix code. And if the lengths satisfy the property I said at the beginning, which is they're all inverse powers of 2, the Huffman procedure will actually give you an entropy achieving prefix code. So we'll see you next time.